Okay, thanks for coming, everyone. It's really cold out today, so it's fantastic you guys brave the cold and be here. So today, I'm going to tell you a little bit about what I can learn as I watch the atoms move. So I'm a material scientist, so I either improve the materials that we already have, or I make new materials. And I look at their properties and see what we can use these materials for. And one way that I study the material is by actually watching these things very carefully using what's called electron microscope. And that's what I'm going to tell you a little bit about today. Okay, let's see. Okay, so let's go back to about 1800s. Mr. John Dalton, he was an English chemist, and he was a bright man, and I think he did a thought experiment because back then they didn't have modern tools that we have. And he postulated that all matter is made up of small things, atoms. He, at that time, thought that these small particles that he called atoms were not, you cannot divide them. So we now know that's not true, but he thought all matter was made up of little particles, atoms. And he thought it can't be that you have too many different atoms. You must have some set of atoms, and if you combine them in a different way, that's how you make compounds, like wood, like coffee, like plastics. So that's what he postulated. And we know that this is true, and we now have a periodic table that gives us about a little over 100 elements, right? So here, this is the periodic table nature gave us. And you can make water. To make water, you grab hydrogen, 2 hydrogen, and 1 oxygen, and that makes you water. If you throw in a carbon to this mix, then you can actually make sugar. So sugar is 12 carbons, 22 hydrogen, and 11 oxygen. And that gives you one form of sugar. And this is something we all love to eat. But now everyone tells you, no, you can't have too much of it. So this is the periodic table. And you know that by combining different elements, you can make different compounds. Now, not only it's important that you bring in different elements, but it's also important to think about how they are arranged, how they're connected together. So this arrangement of atoms is also very important. And I can give you one example. Take carbon. Carbon is atomic number 6. And with carbon, just carbon, you can make diamonds, shiny little objects. And you can take the same carbon, you just arrange them a little bit different way, and then you can get graphite. So when you have your pencil, the black part of your pencil is graphite. So these two cannot be more different from each other, right? Diamond is shiny, light goes through the diamond, and it's really, really hard material. Graphite is black, it's soft, light doesn't penetrate. But it's the same carbon. Now, with the same carbon, you're making 2 different materials, 2 different properties. Very, very different. So how does this happen? It actually happens because carbons are connected to each other in a very different way for these 2 materials. For diamond, carbons are connected in a 3-dimensional fashion with these pyramidal shapes. For the graphite, actually you have these sheets of carbons. Within the sheet, carbons are really strongly bound to each other, and then these sheets are loosely stacked on top of each other. So given the same element carbon, same type of atom, depending on how you arrange them, you get a vastly different materials with different materials properties. So that tells us, gee, not only I have to know what elements or what atoms I have to know how they are arranged. So what do I do? How do I look at them? Now, if you want to look at small insects, you use a magnifying glass, and you look through your magnifying glass, and it gives you about 1 to 10 times magnification. So you can look at small things about 10 times bigger. Magnifying glass gives you about 1 to 10 times. You can use a microscope. So in your school, you use microscope either in biology class or your science class. And this gives you about 10 to 1,000 times magnification. So you can look at small, small things using optical microscope. And can you guess how many times of magnification you need to see atoms? Any guess? Yes. Other guesses? Yeah? 100,000? Do you want to throw some other numbers? Yeah? Trillion? Wow, these are all fantastic. Right now, so starting around 300,000 times, you can see atoms. Generally, about 1 million to 10 million times is what you need. Good job. Good job, guys. So modern technology allows us to go about maximum about 20 million times, but that's an overkill. So when you're about 300,000 to a million times magnification, then you can actually see atoms. So the tool that gives us that kind of magnification is called electron microscope. So here's a one electron microscope. It's a very big machine. So here's a computer screen as a sort of reference point. And using this, you can see things at a 1 angstrom resolution. What is 1 angstrom resolution? Let's think about DNA. We are made up of DNAs. What DNA gives us the codes for the life. It's a double helix structure like this. And the width of the DNA is about 20 angstrom. The distance between the pairs is about 3.4 angstroms. I don't really, still maybe you say, I don't really have a sense of how small angstrom is. It seems very, very small, but how small is it? Okay, our hair, depending on if you have a thin hair or a thick hair, it's around 10 to 50 micron thick. Okay, that's about the thickness of a hair. 1 angstrom is 0.0001 micrometer, which means it's about 10,000 times thinner than your hair. So that's 1 angstrom, okay? So now you can imagine your atom is about 10,000 times thinner than your hair. So that's the reference point. And using electron microscope, we can see that. Let's test that, okay? Let's look at gold. We like gold. Gold is expensive. Gold is made up of gold element, and gold atoms are arranged in this particular fashion to make gold. Now, we can use electron microscope, throw in these gold inside, and you can really see that these are now gold atoms, and they are arranged in this periodic fashion that really tells you that this is how gold atoms are arranged to make gold. Fantastic. So we now know that atomic arrangements are important to give you materials properties, and then we can use electron microscope to look at them. So far, I've only talked about materials where the atoms are arranged in a very orderly fashion. So here, take a look at this. I have 2 different atoms, black and the circle ones. And if you look for a long time, you realize that there's a basic unit that you can repeat forever to make up this structure. And this is an ordered structure, and we call it crystalline structure. Extreme opposite case of this would be that you arrange atoms in a disordered fashion. There's no unifiable unit that you can choose and then repeat forever. So if you have atoms arranged in this disordered way, this is called amorphous structure. Okay? So these are the 2 extreme cases, crystalline structure and amorphous structure. So gold was a crystalline structure. And only recently, I would say about 5-6 years ago, we're now able to see some of the amorphous structure as well. One of the most common examples of amorphous structure is actually glass. Glass is amorphous, where the silicon and oxygen atoms are randomly arranged. Now, if you magnify this about 1 million times, then you can actually see how the silicon and oxygen atoms are arranged. And this is silicon oxide in 2-dimensional form. And you can see that there's no order that you can see in here. Atoms are randomly arranged. So if you zoom in, this is how it looks like. And it's very similar to the amorphous structure that I just showed you. All right. So I'm going to do just a quick recap of what we just talked about. Mr. Dalton postulated, and we now know it's true, that materials are made up of atoms. Not only different atoms, but it's important that how these atoms are arranged, we have to know how these atoms are arranged, because depending on the arrangements, it can give you graphite, or it can give you diamond. Now, and we can see these atomic arrangements using an electron microscope. And this T here stands for transmission, so transmission electron microscope, and in short, we can call it TEM. And 2 extreme cases of arrangements we talked about was crystalline one, where atoms were arranged in an orderly fashion, and amorphous one, where atoms were arranged in a disordered fashion. Any questions so far? Good. OK, so let's move on. So now that I know this, we can use the TEM to not only just watch things in a static state, but I can watch them as they change. So here is one example where this is an ordered state right here. You can see that the atoms are arranged in a very orderly fashion. Up here is a disordered state, and nothing is really clear. And this is a movie that's showing from going from amorphous up top and the crystalline. So this crystalline region is growing into the amorphous region. So that's the movie. And later in the talk, I'm going to tell you a little bit more about this movie. But now I'm going to apply this technique to a modern technology, memory. Okay? So the thing is, we all want more memory. So you can take more photos, store them in your iPhone. If you buy iPhone, you can have an option of buying 16 gigabytes, 64 gigabytes, or 128 gigabytes of memory. Okay? So you have to pay more for more memory, but that's what you get. The technically correct term would be, though, it's storage. Okay? So you're storing your information. So for example, if you took a photo with your iPhone and you store it in your 16 gigabyte memory, and then you turn your iPhone off, your photo is still there. So next time when you turn it on, the photo is still there. So that's why it's called storage. And there's actually a real memory, which is actually just 2 gigabytes, and it's called random access memory. But this is a memory. And it's a memory because as long as your phone is on, that information stays. But if your phone is off, the information that's stored in memory is lost. Okay? So storage stores information even when the power is off, but memory doesn't. And storage, some of us here used to know hard drives and have seen CDs and DVDs. Okay? But for some of the younger friends here, I'm not so sure if you've seen CDs or DVDs, but these are storage, right? We know that we can store information here, and you don't have to have them powered, right? They store information just fine. Leave it, you can leave the DVD room, and that's OK. So the key difference that differentiates between storage and memories is what's called non-volatility. So now that's a difficult word, but non-volatility basically means if your information can be stored, even if you don't power them, that is non-volatile. It doesn't change, right? So storage is non-volatile, and memory is volatile. It's volatile. You have to keep the power on to keep the memory, to keep the information. Anyway, so you see that the storage, we can have a lot of storage, but just a little bit of memory. So this is for the iPhone. If you go to computer, so look at my MacBook. When I look at my MacBook, it tells me that I have 8 gigabytes of memory, and it tells me I have 500 gigabytes of storage. You can buy 1 terabyte of storage. Very cheap these days. OK, but now that's a problem. Because when we do computations, when you're using computer to do programming, you're using memory to do those things. You're not really using storage. Only after you finish the computation, then you save your results into the storage. Okay? So while you're doing computation, you're using memory. So that's a problem because the computing programming is becoming larger and larger. It wants more memory. But the problem is memory is very, very expensive. We just cannot put that many memories into the computer. On the other hand, storage is very cheap. And it's non-volatile, means that you can keep the information even the power is off. But they're very, very slow. So when you're doing computing, you don't want to use storage to do computation, because then it'll be really slow. Memory, even though it's expensive and it's volatile, it's very fast, and that's why we use this. So this has created a really big memory challenge right now. And the way Intel, so there's a big gap. And the way Intel, IBM, maybe Samsung are trying to solve this is that they want to make another type of memory, they call it storage class memory, to fit between these two. And the attributes that they want for this new technology is the best of the both worlds. They want this to be fast, but they want this to be non-volatile, meaning that you can keep the information even the power is off. And they want this to be, of course, cheap as well, so you can have a lot of this. So now everyone is just racing to make this technology real. And one of the particular device that perhaps make this possible is what's called phase change memory. Okay, so I'm going to tell you a little bit about phase change memory now. Phase change memory, to make this, you need 3 different elements: germanium, atomic number 32, antimony, atomic number 51, and tellurium, atomic number 52. So you pick the first letter of each element, G, S, and T, and you call it GST in short. Now, GST is special because even though the compound composition is the same, you can have it in the amorphous state where the atomic arrangements are disordered, or you can have it in a crystalline state where the atomic arrangements are ordered. So we talked about the 2 extreme cases, and GST is a material that can go between these 2 states. And if you measure their electrical property, you find that when the atoms are arranged disorderly, their resistance is very, very high. If you now switch them to the crystalline state where the atoms are arranged in an orderly fashion, then the resistance is very low. And it's easy to go back and forth using a voltage pulse. So you can switch it back to the atomic disordered state. Then the resistance will go back up high again. And this is good because that is how you can make memory. You have one state where the resistance is high, and you have another state where the resistance is low. So that's your memory bit 1 and 0. So this is a memory technology now. So the benefit of then making this memory is that it's very fast. You can switch between these 2 states very fast. It's non-volatile, meaning once you are in the amorphous state, you don't need to keep the power on to stay in the amorphous state. You can take the power off, and then it'll be in the amorphous state. Once you switch to crystalline state, you can take the power away, and it'll remain crystalline state. So that means that the resistance will stay as they are even if you don't power them on. So that's non-volatile. And this, you can make them cheaply in principle because people know how to make these devices very, very small. So you can pack a lot in a small chip. So that can make it very cheap. So this is a good thing. So now, maybe this is how we can solve the energy problem. So what do I want to do? I want to actually use TEM and watch the transition between the 2. That's what I want to do. Now, to do this, I work with IBM Watson Center, and IBM Watson Center is about 1.5 hours away from Yale in Yorktown Heights. Okay? So they make these devices. So here is GST, that's germanium antimony telluride. Now it's in this pillar shape. And then we're switching this between this disordered amorphous state and ordered crystalline state. And we know that as we switch these 2 states for the GST, the resistance value changes. And indeed, they've shown, this is now their data at IBM, the high resistance states, okay? And this is when the atomic arrangements is random, and low resistance states when the atomic arrangements are ordered. And you can see high and back and forth, back and forth. Now, the key metric here is actually the fact that they were able to switch it 10 to the 12th times. So they're reading and writing 10 to the 12 times, which is fantastic. That is a large number. Now, for the memory that I'm using right here, they can switch back and forth 10 to the 15 times. That's the current memory. Okay? Storage, so for your storage, the solid state disk drive that you have, you can switch back and forth 10 to the 6 times. Okay? So that tells you the difference between these things. So for this new technology, even though they showed very good performance, they're about 1,000 times off from their target. Okay? So we have to still reach our target. And perhaps if I watch how these things go between back and forth, maybe we can find a way to reach the target. So that's the goal. My goal is to take TEM movies and watch how the amorphous to crystalline transition happens. Okay? And maybe that can give me a key to how to reach that target goal of 10 to the 15 cycles. Now, this is actually there's a little bit of work that one needs to do. So here is actually the device that IBM gives me. It's a wafer. It's got thousands of these little chips in it. Okay? So I cannot just put this into the TEM, actually. So I have to do some steps. Now, the engineer at IBM tells me, you should look at this particular device. That device was interesting. So then I say, oh, OK. So first, I take this row of device, and I mill away the rest. And then I have this thin slab of devices that I know that this is a target device I want. So once I mill away everything, then I pick it up, and then I drop it onto another substrate that I can now put it into my TM. So here's another image. Okay, it's this slab. Now I'm looking at this inside TM, and it's this particular device that I'm interested in. So the rest, I purposely destroyed, and I'm going to look at this device. This is actually how the chip looks like. The device, you cannot see the device, but the device is right in the center of this chip. Okay? This is now a schematic. This is the electron microscope where I'm now using the electrons. Electrons are going through my sample. This is my device. And that's going to give me TM movies. The TM that I use is actually at Yale. It's in the glass building that's in the Prospect and Trumbull intersection. This is Mike Rooks, who's a fantastic scientist and who runs this microscope and takes care of the microscope. And here's now the movie. So here is the device, and this is just this GSD pillar right here. Okay? Now, I'm showing you the resistance I'm reading here. So in this particular state, it's 44,600 ohms, so 44 kilo ohm. And what you're going to see when I play the movie is that right now it's all kind of gray, and you're going to see that the intensity changes. So some regions of this pillar will turn darker, and that's actually the crystalline state. That's the ordered state. Right now it's in the amorphous state, where the atoms are ordered in a disordered, random fashion. So let's see. OK, so there you go. There you go. So it's now changing between crystalline, amorphous, crystalline, amorphous, crystalline, amorphous. And you see that the resistance value is going high, low, high, low, high, low. So now I'm able to switch the device between the amorphous state, where the atoms are arranged randomly, to the crystalline state, where atoms are arranged in a periodic fashion. And at the same time, I can read their resistance values. And when it's crystalline, the resistance is low. When it's amorphous, the resistance is high. So everything checks out so far. That was about a year's worth of work. Now, so here is a snapshot of the amorphous state. So the atoms are disordered randomly. And this is crystalline state. So you can see that the intensity is much darker. And now these are the resistance values between the high resistance state and low resistance state as a function of number of cycles that we're running inside TM. This is all good. We're very excited that we can do this. And then we found something very curious. So here is one device. We apply a negative voltage to the top electrodes. So that means that the current is flowing to the top. And we see a circle right here where the intensity is a little lighter. And it turns out that this is an empty space. It's a void. There's no material in that particular region. Okay? So that's odd. And that's actually really bad, because that's an empty space. And if you don't do anything, eventually the device is going to blow up. And now your memory doesn't work anymore. So we figured out, so we try to think about, how do we fix this? How do I make this void go away? And then we found out that if you apply a positive voltage instead of negative voltage, then you're going to reverse the current direction. And when we do that, the void went away. The material, which was gone, filled it right back. And science is about being able to reproduce your experiments. So we do it again. So now I switch back to the negative voltage, and voila, the void comes back again. This empty space comes back. I switch back to positive voltage, it's gone. I can repeat it, and it's here again. And it's gone. So we know that this is a very reliable and reproducible, which is good. That's what science is about, right? When you observe something, you repeat it, make sure that this is real. And the resist values changes. So when you have these voids, then the resistances are high. And then when you don't have the voids, then the resistance are low. So we say, OK, this is interesting. We found something that was very interesting. And only by looking at this inside TM, we were able to find this. If you don't do TM, you don't actually know what's happening. So why is this happening? What is a mechanism that makes this happen? it turns out that antimony, when antimony is charged, it is positively charged ion. It's called cation. So because it's a positively charged ion, it likes to go to negative electrode. Because the positive and negative charges, they attract each other. So our theory was, when I put a negative voltage here, then antimony likes to go up. And antimony moves much faster than the rest of the elements. Therefore, I form a void here. So let's see if that idea works. So first, we apply a positive voltage here. It's a little bit difficult to see, but it's positive voltage here. So according to this hypothesis, that means then, if according to our hypothesis, if this is positive voltage and if this is negative voltage, then antimony should flow down. That's our hypothesis. And we can only image where antimony is located. It's a little bit difficult to see, but what we find is that indeed, it's more red here, and that's the concentration of antimony. So the antimony is more concentrated down there than top. So that's OK, seems to hold what we think. So what about I switch the voltage? Now, instead of positive like before, I put a negative here. If I put a negative voltage here, according to our hypothesis, then antimony should then flow upwards, right? So it's the same device. Next cycle, this is what we do. And indeed, that's what happens, that antimony flows up. So it seems that our hypothesis holds that antimony, which is positively charged element, likes to go to negative voltage. And that's how we form voids, because antimony moves so much faster than the rest of the elements. So we found you can form voids, which we want to avoid. But by controlling how you move antimony, you can actually fill the void. And this is not only just an interesting scientific observation, but it actually has some implication for real devices. Because if you have a failed device due to some voids, we now potentially know how to heal that device. Right? Before, if the device fails, that's too bad. But now, maybe you can heal it back up. So the student who works on this project is just, he never gives up, right? So one day, he was doing experiments, and he found this device. Okay? This device is a failed device. This is a large void. In fact, more than half of the device is a void. Right? Now, instead of packing up and going home, he just thinks about what he can do to save this. And indeed, finding out just how antimony movement is important, he's putting negative voltage down here and keeps pulsing the negative voltage until all the element flows and fills the entire device, which is kind of interesting. So you can see that the material is moving, and then at one point it fills the entire device. Okay? Now, so this is a snapshot, right? So there was a huge void, and we keep putting negative voltage here. Antimony is floating, and then now we're moving the element down, and at some point it filled the entire device. And if you look at the resistance values, and the resistance values respond to how the atoms are arranged, you see that at the beginning, the resistance is it's just really high. It's actually an open circuit. There's no current that can flow. And the moment that we fill the entire device, the resistance suddenly dropped. And after that, we were able to switch it back and forth between high and low states. So this, we called it self-healing of a failed device. That even though when you have a failed device, you can heal it. And that concept, at least for the integrated circuits like computers, weren't really applied before. And we were only able to do this because we saw exactly what was happening, right? What was happening. So what does this mean? What does this mean? How does that relate to the target of 10 to the 15 cycles that we want to get to? Right now, the way these devices are run is that you always use a high voltage and low voltage of positive voltages only. Now, that means that if you form the void, there's no way to heal that void because you're only using positive voltages. You cannot reverse the direction of the antimony. So now we think the way to run the device is that you actually have to mix your voltage. Maybe you use a positive voltage, but right after that, you should use a negative voltage so that if the antimony went up, in the next cycle, you move it down, right? So that it doesn't have a chance to form a void. Or if you form the void, in the next cycle, you're going to fill it back up. So we think that this is the right way to run this. You use a positive, negative voltages. And in fact, inside TM, we exactly did this. We used a positive voltage and negative voltage, and we alternated. And then we showed that that's a perfectly fine way to operate your device. So here is my resistances that are high when the device is in the amorphous state, where atoms are ordered in a random when atoms are arranged in a random fashion. And here is our low resistance states when the atoms are ordered. So this is what we think, how people should run the device. OK, so remember this slide? We talked about how the memory is very small amounts of memory, whereas storage is large, but the storage is slow. And everyone wants this new memory technology where it combines all the best properties of these two technologies. And now, by running TEM movies, we think that this material called phase change memory, this memory technology, can really be the way to make this new technology come true. So perhaps we can change the title to Memory Challenge Solved. All right, so I'm going to do a second sort of summary. So in the first summary, we said materials are made up of atoms, and we have to find out how they are arranged. And two extreme cases were that they were crystalline when they were arranged in an orderly fashion, and amorphous when they were disordered. And I applied this to a memory technology, in particular germanium, antimony, tellurium phase change memory, which has this property of when it's in amorphous state, the resistance is high. When it's in crystalline state, the resistance is low. And by using TM movies, we found out how the structure, these structures, and the properties, this is the property, were related. And we now think that GSD phase memory can really solve the current memory challenge. All right. Let's go back to this movie. So this is the third time you're seeing this movie. So what is this movie about? I want to know about this movie. And this movie is really about transition going from the amorphous state to the crystalline state. So as more crystalline state is coming, you get to see these atoms are arranged in a more orderly fashion, and it's growing. Okay? So let's really study this one now. And this one is about studying the dynamics. How does it change from here to here, right? We want to study that dynamics. So this is actually amorphous metallic rod. So it's an amorphous metal. So I don't know if you remember, but at the beginning I showed you gold, and gold was crystalline. All the atoms were arranged in an orderly fashion. But you can also have a metal where the atoms are arranged disordered. Okay? So it's amorphous metal, and you can make them very, very tiny. So these are called nanorods. So remember, our hair is about 10 to 50 microns. So that means that these are about 1,000 times thinner than the hairs. Okay? So you cannot see them with your eyes. You cannot see them with optical microscopes. You need, again, TEM to see them inside a microscope. So here, I then stick these amorphous metals into the TM again. Now they're amorphous, so their atoms are arranged in a very randomly fashion. But actually, atoms like to be ordered. They don't like this random thing. So if you heat them, and if you heat them to give enough energy, the atoms will jiggle around, and they're going to order themselves. Okay? So that's what we're going to do here. Right now, this is about 50 nanometer thick amorphous metal rod. And it's amorphous, so atoms are randomly arranged. And I'm going to heat them. And as I heat them, the atoms will jiggle. And they're going to start arranging themselves in an orderly fashion. And when that happens, you're going to see that the intensity will change dramatically. So let's play the movie. So this is the temperature, 200 degrees Celsius, and I'm ramping up the temperature. And suddenly you see that the intensity changes to very, very bright. So at the time that the intensity changed, that's the crystallization temperature, and that's 255 degrees. What about this one? This one is about 20 nanometers thick here, so it's half the size of this one. So we are zooming in a little bit more. So I'm going to run this one. So I'm ramping up the temperature again, 230. OK, so right there, it's crystallized. And actually, it crystallized at 294 degree temperature, so different from this one. This is a curious behavior, actually, because phase transition is something we know. When water, when it's really cold, water freezes, right? And that's a phase transition going from liquid to solid. And that always happens at 0 degrees Celsius, right? When water boils, that's another phase transition from liquid to now vapor. And that always happens at 100 degrees Celsius. It doesn't matter if you boil water in a big pot, small pot, if I boil it here, if I boil it at home, doesn't matter. It's always 100 degrees Celsius. But here, and crystallization is another phase transition. So from our textbook understanding, it should always happen at the same temperature. But here, this is kind of curious. I just changed the size. I made it about half the size, and suddenly the temperature changed quite a bit. That's weird. Now I have a 5 nanometer one, so that 5 nanometer is 10 times smaller than this one. And when I run this, so here's 100, 200 degrees Celsius. Okay, 250, it doesn't crystallize. Okay, 290, it did not crystallize. Okay, there. This is the crystalline region. So here for this, crystallization temperature is 330. So that's really odd. This is not what I expect, right? I expect the numbers to be same everywhere. It's not. So then you say, why is this happening? I want to really find out why this is happening. So to find out, I zoom in a really tiny region so that I can really see individual atoms. And I'm going to watch how this crystallization happens again. Crystallization means you're going from disordered to the ordered phase, amorphous to the crystalline phase. So now this movie again. So this is really zoomed in image of the previous movie. And now I'm really watching how the crystallization happens. And this time it doesn't play, but then you've seen this 3 times, so it doesn't matter. And I'm going to go to the next slide. Okay. So here's the snapshots, okay? Now I'm taking the snapshot at every second. And you can see the crystalline region where atoms are arranged very nicely, and amorphous region. And because the atoms are arranged randomly, there's no obvious structure that I can find. And these red arrows mark the boundary between the crystalline region and the amorphous region. And I'm doing this at the constant temperature of 360 degrees. And I find something very odd. Do you want me to tell you, or do you want to guess? Yes?
I noticed that one section of each film simply does not crystallize, a thin section on the top.
Oh, you mean here?
Yeah.
Yeah, so that's a good one. That's a very good question. It's because the crystalline region is in the bottom and it's moving upwards. So eventually, like if I go to 15 seconds, 17 seconds, it's going to eventually go all the way.
The time difference between the second and the third is a big jump.
Yeah, right. So here, between 3 and 4 seconds, maybe it barely moves. But between 4 to 5, it jumps really a lot, right? 5 to 6, it jumps, but not as much as here. 6 to 7, it doesn't really jump much, right? That's kind of odd. I expected maybe the rate that the crystallization happens should be constant, because I'm sitting at the 360 degrees Celsius. I'm not changing anything. So if you measure the growth rate as a function of time, you find that it fluctuates. It's not constant. This is very odd. This is not what I learned in high school. Okay, that's very odd. So why is that, right? So this is our theory. Our theory is in the amorphous region, maybe you have some sort of substructure that is maybe a little bit ordered, not really ordered, but just a little bit ordered. So that when you crystallize this much region, and then you do a little bit more crystallization and a little bit more, and when you're now near this substructure, then suddenly the crystallization rate increases. That's our hypothesis, okay? So maybe that's why the growth rate is not constant, but fluctuates, because every time you hit some sort of substructure, you enhance your growth rate. And then maybe the way these things are located, maybe it's random, and maybe that's why it's fluctuating. So that's our hypothesis. So how do I test my hypothesis, right? Science is all about coming up with some hypothesis to explain what you observe and test if that's correct, right? So one way to do it is that you can crystallize this, but not from the glass state, but from liquid. You know, you have a very hot liquid, and you cool it down. And as you cool it down, it can also crystallize. Same material, same rod, but now I start at a very high temperature, and I cool it. 360 degrees, same temperature. Now I cool it. But the idea is, if you're coming from the liquid side down, then these numbers of these substructures will be much less than when you're in the glass state. So that's the idea. So now, if I have a lot less, then I should expect much smaller fluctuations, right? And perhaps the growth rate, the rate at which crystallization happens, should also be lower because I have less number of these. And that's actually what we find. So here, so the blue is for this case, and this is the measurement. So you see that the crystallization rate for this blue case is lower than the red one, which is this one. And then actually, this is in a log scale. So meaning that this difference is actually about 100 times difference. This is a big difference. So indeed, there's no fluctuation. Now, to test this again, I say, OK. So maybe if I have these substructures, what if my metallic rod is smaller, very, very small, so that it doesn't contain any of these substructures? Can I do this, right? So I look at 23 nanometer rod, which is a very small one. And if it's very small, then it doesn't matter if you were starting from glass state or you're cooling down from liquid, because your sample itself is just smaller than the mean distance between the two. And indeed, we find that for these two cases, for this very, very small rods, that their crystallization rate is about the same. And then the degree of fluctuation is much, much smaller. So here, this is actually a 65 nanometer rod, so that's about 3 times larger. This is going from about 5 to 100. That's the level of fluctuations I was seeing here. For this, I'm going from 0.1 to 1. So the fluctuation level is much, much, much smaller, right? So that's my hypothesis. And it seems that so far, everything that I observed seems to really agree that my hypothesis is true. And here is now, I've shown this graph before. This is for the 65 nanometer rod. I've also shown this one, which was for 23 nanometer rod. There were a lot of fluctuations. Now, this is something in between. And then the fluctuation seems to decrease. So everything seems to check out, right? So, so actually, what we found is that what I learned when I was high school was an incomplete picture of how crystallization happens. And in fact, that if you really go down to atomic scale, things are much more complicated, that there could be these random substructures inside that enhances your crystallization rate, even though the energy that you provide by heating this up is constant. So I think that's about wraps up my talk. Summary, the last summary, this is the first summary, right? Materials are made up of atoms. We have to know how they're arranged. The two extreme cases are when they're crystalline and when they're amorphous. And this first example I showed you was that we applied this to a memory technology called germanium antimony telluride phase change memory. This material has both crystalline and amorphous structures. And if it's crystalline, the resistance was low. If it was amorphous, the resistance was high. And we watched TM movies to realize that a void can form, but how to heal that void. Now, the second part of the movie talk was about, you can really do these TM movies at the atomic resolution, actually really seeing how the atoms pop up. And we saw that to study how the amorphous state changes to the crystalline state. And we found, unlike the textbook knowledge, there are small substructures that really accelerate the crystallization speed. Textbook will just tell you that atoms kind of come and they arrange and they crystallize. And that if you hold at the same temperature, then that rate should be constant. That's what textbook tells us. And we found that that's actually not true. And that if you make your samples really, really tiny, then these substructures are absent in very tiny samples. Then your crystallization rate becomes constant, right? So that's what we learned. So if I give this to if I give this talk to my fellow scientists, the conclusion slide would look like this, where I would say property changes, so material property changes, due to phase transformations. The phase transformation we talked about today was amorphous to crystalline phase transformation. And the way I did it was by using a device, which was the phase change memory device, and using an in situ TM. You know, all in situ TM just means that you're taking movies inside TM. And we applied these principles to two cases. One was the phase change memory. And perhaps this, and then I said, you should really alternate your voltage from positive to negative. So we presented a new way to operate the device. And then in the second part, I talked about how substructures, I talked about substructures, and that's actually, scientifically, we call it subcritical nuclei, and how these subcritical nuclei can actually affect the crystallization. So this would be the slide that I would give to the my fellow scientists. So to wrap up, actually, science is never done by one person, right? It's a group of people that do it. And at my stage, I no longer actually go inside TM to do these cool science. It's the next generation of scientists that do it, which are grad students and undergraduate students. So it's a team of people in my group that do the work. Bulk of the work that I showed you today comes from Terry. Terry is a third-year graduate student now. And also Yerin. Yerin is a Yale undergraduate student, a physics major. She's going to junior. She's a junior. So I get to advise these bright people. And my real boss are Andrew and Jane. Jane is 3 and Andrew is now 9 months old. So those are my real bosses. And so with that, and also I'd like to acknowledge my funding sources. All the things that I've showed you actually cost a lot of money to do. So Yale was very generous in providing a lot of equipment and also research fund, and National Science Foundation, and also Department of Energy, and also IBM, who I collaborate with. So with that, thank you very much for your attention.
And then don't leave, remember we have our raffle at the end of the day because we were looking at atoms. We got a cool microscope as our grand prize, I think. Okay, questions? Here?
If you're saying only the S part of GST moves, what are the other GNT doing in there?
Okay, great. So I'm going to repeat the question. So the question was, for the germanium antimony telluride, if only antimony moves, what about the germanium and tellurium, right? So, okay. So one thing, I'm working with a company. So company doesn't like to share all the little secrets that they have developed. So even though it is, it probably contains all the 3 elements, I think germanium is mostly not there because I just don't see them much in the TM. So then it leaves only antimony and tellurium. And if you look, actually, antimony is so much more mobile than tellurium, so that it's whatever that moves faster that basically controls the property. So the tellurium, it moves. We can check that, but not as much. Yeah. So as I change the voltage, it still seems kind of uniformly distributed for the tellurium. Yeah. Yes. Oh, sorry.
Is there a reason that the antimony moves faster than tellurium?
That's a fantastic question. So how do I tell which atom moves faster, which element moves faster? That is a deep question. So for this particular one, I cannot tell you. So, but we know, so generally we know that copper likes to move really fast. We just know it, right? So sometimes finding out how maybe one element moves faster than the other, you have to find out what are the bond strengths between atoms, right? Sometimes they're really bound strong, which means that it's not going to move fast. Other times they're bound loosely, which means that they're going to move fast. Metallic atoms usually are somewhat loosely bound. So if it's a metal atom, then they move much more faster. And antimony is a metal atom. And tellurium is not a metal atom. So that could be one reason. Yeah.
How close are we for having GST technology in phones?
Okay, oh wow. So you can actually buy a memory card based on phase change memory right now. You cannot buy what I call storage class memory. They want this out in the next 3 to 6 years. So when I'm working with IBM, they're really making a big wafers, and they're testing all the time. So they have the technology down, right? So they are able to switch 10 to the 12 cycles. They want 10 to the 15. At the rate they're going, I think within a year or two, they'll get there. But then the problem is, you want to be able to do this reliably, right? You want, when you're fabricating these devices, you want 99.9% reliability, right? And that can be a tough problem to solve. But in terms of the technology itself, they've gotten it down. So the next 3 to 6 years is their sort of target time frame. So invest in stocks if you have some. What is my favorite element? Oh, wow. OK, what is my favorite element? Right now, it's tellurium. And the reason is that, so one of the elements I showed you was GST. It has tellurium. The another element I'm studying, the another compound I'm studying a lot is tungsten telluride, which is tungsten and tellurium. Another one I'm also studying is tin telluride, so it has another tellurium. So these days I'm studying quite a bit of tellurium, which is somewhat unfortunate also because tellurium is a very rare element. Earth doesn't have a lot of it. So you can't probably think of an application where you need a lot of tellurium. But for maybe niche applications, it's still OK. Who's taking questions? Are you?
In your second example of the TEM movies, you noticed the subnuclei for accelerating the crystallization speed. They look like seeds. They look like crystals which form off of seeds. Do you know the nature of these subnuclei? Do you know anything about those?
So that's my next question. I have no idea what they are. I'm just calling it substructure. I'm calling it subcritical nuclei. It sounds fancy, right? I have no idea what they are. So it could also be chemical fluctuations. Actually, these amorphous metals have 4 different elements. It has copper, nickel, phosphorus, and platinum. So it's possible that for these subcritical nuclei, maybe the chemical composition is a little bit different there. It's also possible maybe the chemical composition is uniform everywhere, but then the structure is a little bit different. So right now, we're planning some experiments at a national lab. We're going to go to Oak Ridge National Lab, where they have some 3-dimensional chemical imaging tools. So we can precisely answer that question. So right now, the experiments are scheduled for June. So we have to wait for June. Yeah. Yes, that is a fantastic question. Yes, usually they're always more compact. OK. Mostly, usually that's true. I think you can still have special cases where that's not true, but that will be a special case. Yeah.
Like water.
Yeah. Yeah.
Actually, 2 quick questions. First one, there was a picture where you showed like the concentration of antimony. So you can see it's a mix of atoms, right? So how is it possible that you say that this is the concentration? Is it a feature of TEM? And the second question, did you by any chance work with nitinol and structure? Nitinol.
What's nitinol?
Nickel to titanium.
OK.
Memory alloys.
Oh, OK. So the first question is, how can you only image antimony?
Yes.
So that's a special mode of TM. So TM, when I do atomic resolution imaging inside TM, there are many different modes. One of the modes is that so in TM, I'm using electrons as my source, and the electrons come down at a really fast speed. It goes through my sample, and I'm collecting the electrons that have been transmitted through the sample. the electrons are so fast that usually it doesn't really interact a lot with the materials. But sometimes the electrons will come and knock off an electron from an antimony. Antimony itself has a lot of electrons, and this incoming electron can knock it off. As the incoming electron knock off, say, one of the antimony electron, then it has now lost energy. So I can also do some imaging where I just look at, I'm only going to collect electrons that have lost certain amount of energy. And that certain amount of energy I know corresponds to interaction with antimony. So by collecting a subset of electrons, I can form an image only for the antimony ones and also for tellurium ones. So that's how I did it. Second question about nickel titanium. No, I think oftentimes each compound has its own so many peculiar things that at least for me, it takes time for me to learn about one compound. And as one bright young friend asked, right now my favorite one is tellurium-based compounds, and that's what I'm focusing on. Yeah.
What's so special?
What's so special about tellurium? It's not that something is special about tellurium. It happens that all the compounds that I'm studying right now happen to have tellurium. Now, maybe one thing I can say about what is so special about tellurium is that people who compute material properties, people can use theory to predict materials property. And we've now gotten the point where we can handle some of these heavy elements very well. Before, we couldn't handle heavy elements very well before, computation-wise. But now we can. So we're starting to look at compounds that contain heavier and heavier elements, which maybe 10 years ago, we just simply didn't. So now that we're looking at heavier elements, we're finding new novel properties. Yeah.
Okay, one last question here from the audience.
Where does the tellurium come from?
It is in the Earth crust, so you can dig it up. I think people don't mine tellurium for itself. It's usually a byproduct of some other processes, but I don't actually know. Yeah, but it's in the Earth crust. Yeah. Yeah.
So I'll take the last question. So you said that the other thing about your phase transitions is that they didn't happen all at the same temperature. Right. So you looked at the rate, but you didn't say anything about why they didn't happen at different temperatures.
You know what? It actually turns out that it's because as you make it smaller, the number of substructures that you have become different. That's actually it. So here, right here. Yeah, no, not Gibbs-Thompson. Not Gibbs-Thompson. We checked that. So Gibbs-Thompson effect is there, but not that. So here, 50 nanometers won't have much more substructure. That's why the crystallization can happen faster. That's why the temperature is lower. That's it.
An implantation and make some extra defects to see if you could artificially change it without changing the size?
So the way we want to study it is actually, I want to be able to directly see this, like right here. Yeah. I want to see this. I think if I can see this, that would be fantastic. So that's the Oak Ridge lab experiment. Cool. Yeah.
All right, let's thank everybody.